Applications of Laplace transforms in circuit analysis. The Laplace transform is a powerful method of solving a linear differential equations, as the transient response of an electrical circuit can be described by a linear differential equation. Hence, the Laplace transform finds its application in solving the transient behavior of the electrical circuits. The Laplace transforms automatically takes care of initial conditions without any necessity of the first determining the general solution and then obtain from its particular solution. Laplace transformation also provides the direct solution of non-homogeneous differential equations. The essential steps consist of the differential equation is transformed into algebraic equation. The second step, the algebraic equation to be solved, and the next step, the solution is transferred back in such a way that it becomes the required solution of the differential equation. So here the first step is transformation from differential equation to algebraic equation and solving that algebraic equation to get a solution. That solution is transferred back into required solution of a differential equation. Now the Laplace transformation of a function f of t is represented with capital letter F of s, which equals to integral 0 to infinity f of t of e power minus st of dt. Let it be equation 1. S being intermediate or transformed variable, whereas f of t is a time function, must be multiplied by the exponential function e to the power of minus st. Then integrated, then f of t is obtained from t is greater than 0. And if the t is less than 0, the function f of t is 0. Laplace transformation of f of t is in the complex frequency domain, or simply we can call this as S domain, where the complex variable is the S given by rho plus j omega, where rho is the real part and j omega is the imaginary part. In electrical engineering, for most of the function, converges can be assumed provided that the real part of the function is positive, which in this context provides the real of S. Now, the inverse Laplace transformation permits going back into the reverse direction from S domain to T domain or time domain. Simply you can call this as from complex frequency domain to the time domain. That is inverse Laplace transforms, represented with L inverse of the f of s is equals to the f of t, which we are going to get, given by 1 by 2 pi j integral rho naught plus j omega rho naught minus j omega f of s multiplied by e st ds. Let this be equation number 2. Laplace transform of a derivative. Now we know that the Laplace transform f of t is given by the integral 0 to infinity f of t e power minus st dt. To solve this, we have a formula that integral u dv equals to uv minus integral v du. Here u equals to f of t. Now du by dt is equals to f of t, from which du equals to f of t dt. We can represent this with f dash of t. Now we know the u and we know the du. Now we need to know the v. The v is given by e power minus st du. To get the v, integrate on both sides. Now integrate e st du. Then you are going to get v equals to e power minus st. You are going to get minus 1 by s. This is v. Now substitute this. Then you are going to get Laplace transform of f of t, which is nothing but capital F of s is equals to the u is f of t and the v is nothing but minus e power minus st by s minus integral v is again here minus e power minus st by s, and du is f dash of t dt minus f of t divided by s e power minus st from 0 to infinity plus 1 by s of integral 0 to infinity f dash of t e power minus st dt. The infinite value will be 0, then the 0 value f of 0 divided by s here plus 1 by s of integral 0 to infinity f dash of t e power minus st of dt is equals to f of s. Now s of f of s equals to f0 plus this is 0 plus integral 0 to infinity f dash of t e to the power of minus st of dt, or simply integral 0 to infinity f dash of t e power minus st dt is equals to s f of s minus f at 0. Let this be question number 4, where this is number 3. Observation of equation number 4 reveals that this expression gives the expression for Laplace transformation of derivative of ft, that is Laplace transformation of being f of t by dt is equals to Laplace transformation of f dash t e power minus st dt. Let this be equation number 5. Then, thus the equation number 4 can be written as Laplace transformation of f dash of t is equals to s f of s minus f of 0 plus. Let this be question number 6. Laplace transform of integral f of t dt is given by integral 0 to infinity integral f of t dt of e power minus st dt. Now let u equals to integral f of t dt and dv equals to e power minus st dt. Now the integration by parts is going to give us the Laplace transform of integral f of t dt equals to u, that is integral f of t dt multiplied by minus 1 by s e power minus st between 0 and infinity minus 0 and infinity minus 1 by s e power minus st of f of t dt, that equals to 1 by s integral f of t dt. This is for 0 plus and minus of minus plus 1 by s e power st f of dt is nothing but f of s. Let this be equation number 7.